Hello there, physics class. Today I'll be kind of brief. I wanted to keep it brief because some of you, because for whatever reason, you're able to make it to lab through Zoom on Friday. But you should have gotten the email by now and be just about done that. But I do need to keep us moving forward on material. Do please make sure that you, quote unquote, show up to class every day, watch a video, fill in the forms, read your book, make sure that you're doing all the things that you need to do, and keep up with the assignments. All the homework is going to be due next Monday. That would be April 6th. We will be then also working on trying to get an in-home project done, so I'm kind of looking forward to that. I think it's going to be good. All right, so we're going to talk about machines today, and so machine is a device that's used to help do work. In other words, it can be used to make your work easier. Now, some machines do this in one way and some in another way, so I want to talk a little bit about what it means as far as making your work easier. So one thing a machine can do is multiply force. Okay, so the thing with multiplying force is that, for example, when you use a car jack to try and lift up a car, you are not capable of lifting that car all by yourself, and so you use a machine to help you out with that, and you can push on one thing and every single one of you, including myself, is capable of lifting a car if I have the right machine to do it. A little later in the week, we'll have a video that I'll have you watch to demonstrate this. If we were in school, we'd be out taking my car and practicing lifting it up using this process, and I'm hoping that we get back before the end of the year to be able to actually do that in person. But if not, I'm going to find a really good video for you to be able to watch and learn for that eventuality, just in case. So multiplying force is one thing that a machine can do to help you. Another thing is that it can multiply distance. There's a certain way a force can be applied, and you're really strong and you can apply a big force, but you need to make that distance extend. So for example, if you're taking a swing with a baseball bat and you are really, really strong, you can swing that thing hard, but the idea is to transfer that force to the ball and make the distance extend, even though the force has diminished in some way. And then another thing that a machine can do, it can change the direction of force. So for example, if you've got a pulley that's that you're using, or you've thrown a rope up over the top of a tree limb and you pull on it so that you're pulling something up because it's more convenient to do that, or you can put your whole weight into it that way. Just a way that you can change the direction of force. That's another good thing that a machine can be used for. Now, direction can be changed at any time, but you can't both multiply force and distance at the same time. One can happen or the other can happen, but not both. So this leads us to discussing what these forces are, and then also how they look in an equation or an expression to help us to figure out what kind of an advantage there is to doing these things. So we need to be able to identify in any machine what the effort force is. So in other words, you have to put in an effort to make the machine work. In the case of a car jack, you're probably going to push on the handle. In the case of the baseball bat, you're putting the effort to swing that bat. Various different things, and we will talk about them really mostly tomorrow, but this is just to get you going. So with the effort is what you put in, and we will designate that the force due to effort, Fe. The resistance force, okay, resistance is actually what comes out of the machine. Okay, the word resistance sometimes doesn't make us think of the right thing, but when I'm thinking about it and I see FR, even though it's technically resistance force, I usually think the result. So in other words, what force came out of the machine? What was the result in terms of force as the force came out of the machine? So for the case of my car jack, I've put in my effort, which is me pushing on the left, and the resultant force or the resistance is that car being lifted up. So you have these things that we can think about. If you compare the amount of resistance to the amount of effort force, what we end up with is what's called the mechanical advantage. And the mechanical advantage is basically a multiplier. It's how many times that effort ended up getting multiplied. So if we, if you think a little bit about this, if we had the mechanical advantage times FE, that would give you the result or what happened. The way that you calculate it is if you know the result, or you know what's called the resistance, and you know the effort, you can take that divided by that, and it will give you this quantity that we know called the mechanical advantage. Now, since it's newtons divided by newtons, this is going to be a number without a unit. All right, it's really just a multiplier called the mechanical advantage. So if the mechanical advantage is greater than 1, in other words, what comes out is greater than what went in, then that means that FE got multiplied. Okay, the effort was smaller and you got a bigger result. If the mechanical advantage is 1, that means that both are equal. You would have a situation like that where if you just used a pulley and you just changed the direction of force and there was not even any friction in the pulley, anything like that, the mechanical advantage could be 1, where these two numbers are equal to each other. If the mechanical advantage is less than 1, it means that you lost some of the force. The force decreased, which, as I said in the case of the baseball bat, the force decreased, but you're exchanging that for distance. Same thing with like a wheelchair ramp. You've got a wheelchair ramp, so you're having to take this thing that if you needed to lift straight up, that would be an awful lot of force, but since you can spread it out over a greater distance, you can have your effort multiplied. That's actually more like the first one. But mechanical advantage being less than 1 means that the force that you input ends up being diminished in some way. Okay, so as in anything, there is an ideal. And the ideal means perfect. No friction. So none of the work is lost. Now, work is something different than just playing out the force. Work is force times distance. So WO stands for work out. WI stands for work in. So if the work out equals the work in, then that's ideal. That's perfect. There's no extra credit in machines. Okay, so you can't have more work out than the work that was put in. So you have resistance force times the resistance distance, or in other words, the result force times the result distance has to equal the effort force times the effort distance, what went in. Now notice that I have a little bit of a cross out here, because what I wanted to do is I wanted to divide both sides by FEDR. Okay, now the reason that I did that is because in this case these cancel out, and that gives us FR over FE, which, if you remember, FR over FE is our mechanical advantage. So in the ideal case, what we find is that this equals DE over DR, the effort distance over the resistance distance, and that gives us a quantity called the ideal mechanical advantage. Because sometimes you don't know the forces, but you do know how far something moved before, how far the input force moved, and how far the thing that happened afterwards as a result, or the resistance, moved at the end. So the ideal mechanical advantage is like this. All right. And then we have another concept called efficiency, where if something is more efficient, you talk about in life something being more efficient, that means that you have less of your work wasted. And that's really how this works. If you have a perfect machine, it's 100% efficient. That would mean that the work out compared to the work in was 1. Okay, all the work in translated into work out. So you would have 100% efficiency because you would divide these out. But this works, like let's say, for example, instead of having all the work you put in come out, some of it might have been lost for friction, so you end up getting less distance out, or it loses a little bit of the force. So you could have work out divided by work in and get a fraction of what you started with times 100 would give you your percent efficiency. Another way is that if you know the real mechanical advantage compared to the ideal, then you can also calculate efficiency that way. And then also what you can do is you can use the quantities that represent mechanical advantage and ideal mechanical advantage, and you can put them in and go directly to the answer if that's the information that you have. Tomorrow we're going to talk about the 6 simple machines and where these effort forces and where these resistance forces are when you're using them. And we'll be able to do some example problems, and hopefully by then you'll be caught up with your lab and we'll be able to move forward with that. So this is all I have for you today. I miss you guys a lot, and I can't wait to get back to real school. Real in-person school. This is real school. It's just with this, especially with this mechanical bent that we're taking right now, it would be great to be able to have you actually move some things. So we're gonna be working on that at home. So just stay tuned for that. In the meantime, you might want to collect up things that you could use to make some kind of a device that could do some work for you. And I'll get back to that, but just as a little bit of just as a little heads up on that. And you probably saw on your GradeLink assignments, you've got something coming up. But we will talk about that in length as we go over the next few days. But anyway, for right now, have a great day, and hopefully I'll be seeing you soon.